Right, so I'm Gašper. I work on software ecosystems, which is a fun job full of herding cats, not Dan. And I'm gonna hopefully relate to you some things that I learned along the way. And it begins with jazz. So Miles Davis, a legendary programmer, once said, it's not about the code you write, it's about the code you don't write. He was a really good jazz musician, for the people who don't know, and this is the actual quote that's up there. And for a long time, because I'm also a musician, I thought that he was just being really clever. Like, oh, no, like, you play on the audience's expectations, like, they know how the song goes. You're not going to play that note. You're going to play something else. But then lately I started to understand this quote very differently. Because jazz is known for its improvisation, right? And so it's not really about the notes that you play when you're improvising as far as your band is concerned. It's about the notes you promised not to. Because you pre-agree on a chord progression. Right? Like, if you want to keep in harmony, you have to not play certain notes. You can play anything else you like, as long as you stay within the chord progression. And then you can play with the audience's expectations and play the blue note, which is why it all works. So the point is really, it's about the things you say you won't do. Which brings me to shapes of balloons. Your project, when you're starting out, is like a balloon. It's happy, you're inflating it, it's filling space the way a balloon does. But unfortunately, your design space only looks unconstrained when you start. Pretty soon, it starts looking a lot more like this. You have some obstacles in the way that are inherent to where you are, and your balloon is eventually going to hit them. And then it becomes really, really important where you started. Right? Like, if we started above, our shape is going to be very different than if we started in the middle of the two obstacles. And sometimes we can choose the obstacles we're going to encounter along the way. And so this is what this talk is really about. Because once you start doing this, you will never move this balloon ever again. It will become extremely, extremely difficult because your balloon has adapted to the shape of the obstacles, and if you discover that your customers need your balloon to be somewhere else, you're going to have a bad time. So, a case study is our dear Unix file system semantics. In the olden days, CPUs were 1. And so, of course, in Bell Labs, they were really concerned with mostly inter-process communication, and the file system seems like the natural place to put it because you didn't have a lot of RAM, it like auto-spilled, it was kind of nice, right? And so, how do you make sure that two processes know that one has finished its stuff? Well, you use a lock file, obviously. You can communicate over pipes. You can set up FIFOs. Where are they? On the file system in a directory. They have an inode. Lovely. We have this unified namespace. Everything agrees on it. It's wonderful. Except then scaling happened. So this happened. NFS stands for not a file system. Because it doesn't obey any of these principles, or it tries to, but it fundamentally runs into the issue that networking is an unreliable medium. It also runs into the issue that you don't have a single broker, right? Like, even on one machine with multiple CPUs, the kernel can keep the semantics of your file system to the promises that it notionally has to keep, because there is a single broker, even if you've got a fancy NUMA thing, right? However, NFS is not so lucky. And so you have to inevitably make some decisions. Now here I want to take a quick digression to Lisa, who's over there, who coined this really wonderful concept in her talk at C++ Now, what she calls Slack. When you have an interface, there's the in front of the interface and there's at the back of the interface. And if your implementation conforms very strictly to the interface, like the balloon hugging it, you can't move. You are forced to just implement the interface, and like that's where it is. You have hit Hiram's law, right? Same for the users of the interface. If they hug your interface really tightly, they can't move either. So she illustrated this in her talk with some ropes, who also have a natural idea of Slack. But the point is really like, who owns the Slack? Like, whose Slack is it to consume? And that's where the interface is the real delineation of who owns the Slack, right? Going back to our dear file system and not a file system semantics, the problem really is this CAP theorem and its actual practical application, which is called PAC-ELC for people who are paying attention. I have 20 minutes. I'm not going to go into that. But the point of the theorem is that you have these three obstacles or features that you might want to have in your distributed system, and their consistency, availability, and partition tolerance. And it's like, here's three, pick any two. And the problem is partition tolerance is not really up to you because you're going to have partitions. It's the network. And so you're really choosing between availability and consistency because that's just how it is. So this is what the choice looks like for file systems, for NFS, usually. You have to choose consistency because that is what Unix promises. And then availability takes a dump. Right? Like, unless you confirm every single thing that you do with your file system with the filer that you have, you do not get Unix semantics, which means your file system will lock up and your clients will be unhappy. So this is what you try to not do. And for years and years and years, and even to this day, we have tried to solve this problem that is fundamentally unsolvable. Until somebody at some point had a grand idea that we should do this. So let's prioritize availability and make the things that we don't really need to be consistent eventually consistent. Because the things that Unix really promises you to be consistent are operations on a single directory. Right? Like creation of inodes, deletion of inodes, they all have to be sequentially consistent because otherwise lock files don't work. You can't do negative caching because everybody's polling for the damn lock file. And so if you have a negative cache, then it just won't exist for the next 5 minutes, which is great for everybody's workloads. And so if we had an object store that just said, you know what, like listing directories, we don't need that shit. We might want consistency on a single object, and even that's not guaranteed for every object store. It depends on your particular product that you have chosen or implemented. But this fundamental relaxation of, you know what we will not do? Directory listings. That is the entire thing that determined a type of product that fits scaling much, much better. And the point of this is not that I think object stores are great, they have their use, but the point is, it's the thing you choose to promise to not do so that your users know not to rely to it, that fundamentally determines the final shape of your product once you have filled the design space with development, right? This is very expensive. Doing this is extremely expensive. But this is what we're effectively asking people to do when we're asking them to move from using a file system to using an object store, just from the other side of the boundary. And so this is why for workloads that grew up before object stores or were too small to need an object store to begin with, because everybody starts with the file system, this is why you end up in the NFS trap. Right? Everybody starts small and they just get something working and doesn't plan to need an object store, and all of a sudden, this gets expensive. Which is why you need to plan ahead. Otherwise, it will get too expensive to do, and this is why NetApp has a great business model. So I want to say a little bit more, and thank you to Lisa again for showing me this guy's work. This is Wesley Newcomb Hawfield, who died in 1918. He was a legal scholar in the US. And he had this wonderful idea that he wants to classify things that people talk about when they talk about legal agreements. Turns out the legal profession wasn't exactly excited about this because the legal profession depends on creative misunderstanding of contracts. But it works really well for us engineers because we actually try to cooperate to get things to work, right? And so he said that there's these 4 fundamental things that always exist in pairs. Like if I have a right, then somebody has a duty to provide me that right. If I have a privilege, that means that somebody else has no right to impinge upon me, and so on. For proving programs, we use 4 of these entries. But today I'm actually going to be talking about ones that Lisa doesn't really use in her theory, because they're a little bit different. So when we talk about file systems and object stores, right, like we have the implementer who promises to the user to do something, and then the user can expect that that will be fulfilled, okay? Or the implementer can affirmatively say, I make no promise to do this. And then the user cannot count on it. And these are precisely the duty right and privilege no right relationships. It is the privilege no right relationship that grants you, the implementer, the slack to do things later. So as I do, I think about things that I see, and sometimes they don't let me sleep for a while. And I was thinking, you know, Conway's law, which is an adage that says, you know, like your software architecture is doomed to have the same architecture as your communication architecture of your company. And I'm like, yeah, I mean, we all see this happening over and over again. It's such a truism, but why? Like, why is it inherent? Turns out it's the CAP theorem. Yeah, it's, again, the consistency, availability, and partition tolerance theorem, just applied to the distributed systems of parts moving between parts of your organization. Because you have an implicit movement boundaries, think network link, between ownership boundaries. Because every part of the ownership boundary has its own, you know, to-do list that they're working on, and they can't move consistently. So they can't choose consistency most of the time, otherwise it gets very expensive. Availability is not really up for grabs in an organization because you can just look at it. Like the program is there, like the design is there. It's not really sort of like partition tolerance. It's kind of in the background in this particular case. So you have to say, well, we just have to handle partition tolerance, right? Like we are forced. And that is why you get partition tolerance between different parts of your organization. It falls out of math. And so that finally kind of explained it to me, and I was happy and I could go to sleep. But you find these kinds of interdependent constraints all over the place. So what I'm trying to tell you is when you're setting out on a new project, see the final shape of your balloon. Anticipate which walls you're going to hit. And the most important part is to defend your design slack and choose your constraint space as early as possible. That's it.